Light travels at 670 million miles per hour. Nothing in the universe moves faster. Scientists call it the cosmic speed limit, the absolute maximum velocity anything can achieve. Your brain registers this number and assumes light is impossibly fast. You are wrong. If you could travel at light speed toward the nearest star beyond our sun, you would need over 4 years to arrive. 4 years moving at 670 million miles per hour just to reach our closest stellar neighbor, cross our entire galaxy, and the journey stretches to 100,000 years. Reach the nearest major galaxy, and you are looking at 2.5 million years of travel. The speed of light is not fast. It is horrifyingly, catastrophically slow, and that changes everything about our place in the universe. If you want to understand why the universe's ultimate speed limit actually traps us in cosmic isolation, hit that like button and subscribe. This journey will change how you see every star in the night sky. Now, get yourself comfortable. Let's begin. Light moves at 299,792,458 meters per second. Scientists confirmed this measurement with extraordinary precision using atomic clocks and laser interferometers capable of detecting variations smaller than a single wavelength. That number translates to roughly 186,000 miles every single second. In the time it takes your heart to beat once, light travels far enough to circle our entire planet more than 7 times. 1 heartbeat, 7 trips around Earth. Your intuition immediately registers this as impossibly fast. This velocity exceeds anything humans have ever directly experienced by margins that strain comprehension. The fastest aircraft ever built, the North American X-15, reached speeds of 4,520 miles per hour during test flights in the 1960s. Light moves approximately 148,000 times faster than that experimental rocket plane. Light outpaces the space shuttle by a factor exceeding 10,000. Even the Parker Solar Probe, humanity's fastest spacecraft ever constructed, maxes out around 430,000 miles per hour during its closest approaches to the Sun. This probe falls toward our star, using solar gravity to accelerate to velocities no human technology could otherwise achieve. Light still beats it by more than 1,500 times. The fastest object humanity has ever built moves at less than 0.1% of light speed. Your intuition screams that such velocity must represent ultimate speed, the kind of motion that renders all distances trivial. Point a flashlight at the moon, and the photons arrive in just 1.3 seconds. That beam crosses 239,000 miles in barely longer than a single breath. Bounce a laser off the lunar reflectors left by Apollo astronauts and the signal completes its round trip in under 3 seconds. Scientists use this technique to measure the Earth-Moon distance with millimeter precision. At these distances, light seems instantaneous, godlike in its swiftness. Turn on a lamp in your living room, and the light appears to fill the space immediately. No human sense can detect the delay between flipping the switch and illumination reaching the far wall. Electromagnetic signals carrying your voice during phone calls cross continents in milliseconds, delays so brief that conversations feel instantaneous despite spanning thousands of miles. Light appears to move infinitely fast for any practical human purpose. But this perception represents one of the most dangerous illusions in human understanding of the cosmos. We evolved on a planet roughly 8,000 miles in diameter. Our brains developed to comprehend distances measured in footsteps, in days of walking, in horizons visible from hilltops. The savanna environments where human cognition emerged stretched perhaps dozens of miles in any direction. Nothing in our evolutionary history prepared us for scales where light speed becomes pathetically inadequate. The human brain processes spatial relationships using neural architecture optimized for terrestrial navigation. We judge distances by how long walking would take, by how objects appear to shrink with separation, by familiar landmarks that provide scale. These cognitive tools work brilliantly for hunting, gathering, farming, and building civilizations on planetary surfaces. They fail catastrophically when applied to cosmic distances, where the numbers exceed what neural circuits can meaningfully represent. Watch the sunrise tomorrow morning. That golden light warming your face left the sun's surface 8 minutes and 20 seconds ago. The star you see hanging in the sky does not show you the sun as it exists right now. It shows you the sun as it existed nearly 9 minutes in the past. The photons entering your eyes began their journey when you were probably still asleep, racing across 93 million miles of vacuum while you dreamed, showered, and prepared for your day. If the sun suddenly vanished from existence this very moment, you would continue seeing it shine for over 8 minutes. Earth would continue orbiting a star that no longer existed. Plants would continue photosynthesizing sunlight that had already been emitted before the sun disappeared. Only after 500 seconds would the last photons arrive, the sky would darken, and simultaneously, Earth would fly off into space as the gravitational influence also ceased. The sun could be gone right now and you would have no way to know for another 8 minutes. This delay seems minor, almost trivial, until you extend the same logic across our solar system. Light from Jupiter takes between 32 and 52 minutes to reach Earth, depending on where both planets sit in their respective orbits. When Jupiter appears closest in our night sky, its light still needed over half an hour to arrive. When it sits on the far side of the sun, nearly an hour passes between the light's departure and its arrival at your telescope. When NASA controllers send commands to rovers exploring the Martian surface, they wait between 3 and 22 minutes for signals to arrive depending on orbital positions. A command sent to Curiosity or Perseverance cannot receive confirmation of receipt for at least twice that delay. If a rover encounters an obstacle, controllers on Earth do not learn about it until minutes after the event occurred. If they send instructions to stop, those instructions take additional minutes to arrive. Communication becomes a frustrating exercise in patience rather than conversation. Every exchange requires planning for delays that dwarf human attention spans. The outer solar system reveals light's limitations more starkly. Photons from Saturn need roughly 80 minutes to reach our telescopes. The ringed giant we observe tonight displays conditions from an hour and 20 minutes ago. Light from Uranus travels for nearly 3 hours before reaching Earth. Neptune's pale blue glow requires over 4 hours to bridge the gap. The ice giant we photograph shows us ancient history by the standards of human activity, though merely moments by cosmic measure, and Pluto, that distant dwarf planet orbiting at the frozen edge of our solar system, sits so far away that light needs roughly 5.5 hours to make the journey. When New Horizons spacecraft flew past Pluto in 2015, the confirmation signal took 4.5 hours to reach Earth. Scientists who had worked decades on the mission had to wait nearly half a day to learn whether their spacecraft had survived the encounter. The celebration erupted hours after the actual flyby had concluded. The Voyager 1 spacecraft, launched in 1977, has travelled farther from Earth than any human-made object in history. After nearly 5 decades of continuous flight at 38,000 miles per hour, it has covered roughly 15 billion miles. This distance exceeds comprehension through normal reference points. If you drove a car at highway speeds toward Voyager's current position, you would need over 25 million years to arrive. Yet light crosses that same 15 billion miles in approximately 22 hours. A signal sent from Earth to Voyager 1 right now would not arrive until tomorrow. The spacecraft's response, travelling at the same light speed, would not reach Earth until the day after. A simple exchange of data requires 2 full days of waiting. Engineers who send commands to Voyager must plan 2 days ahead, anticipating what the spacecraft will need before receiving confirmation that previous commands executed successfully. This might seem like a reasonable inconvenience for a probe at the edge of interstellar space. After all, Voyager has travelled for nearly 50 years to reach its current position. 2 days of communication delay seems proportionate to decades of travel, but here is where human intuition completely fails. Voyager 1 has barely scratched the surface of interstellar distances. After 50 years of continuous flight, After covering 15 billion miles, after traveling farther than any human artifact in history, Voyager has completed less than 0.1% of the journey to the nearest star. The nearest star beyond our Sun, Proxima Centauri, lies approximately 25 trillion miles away. That number contains 13 digits. Writing it out fully would require 25, followed by 12 zeros. Voyager 1, travelling at 38,000 miles per hour without stopping, would need over 73,000 years to reach Proxima Centauri. The entirety of human civilization, from the first cave paintings to the smartphones in your pocket, spans roughly 50,000 years. Voyager would need longer than human history to reach the closest star. Light requires 4 years and 3 months to cross that same distance. 4 years, moving at 186,000 miles per second. 4 years at a velocity so extreme that nothing in the universe moves faster. 4 years racing through the void between solar systems at speeds that make our fastest spacecraft look stationary. Contemplate what this means for any dream of interstellar exploration. Even travelling at light speed, the absolute maximum velocity physics allows. A journey to Proxima Centauri would require over 4 years of continuous travel. Any crew attempting this voyage would age more than 4 years during transit. Children born at departure would enter kindergarten before arrival. Messages sent home would take over 4 years to reach Earth. Responses would require another 4 years to return, an 8-year communication loop for our closest stellar neighbour. And light-speed travel remains forever impossible for any massive object. Einstein's physics demonstrates that accelerating mass to light speed would require infinite energy. No civilization, no matter how advanced, can push spacecraft to the cosmic speed limit. The best any technology could theoretically achieve remains some fraction of light speed, extending journey times proportionally. But Proxima Centauri is practically next door in cosmic terms. It sits close enough that its gravitational influence barely separates from our Sun's domain. Most stars visible to naked eyes at night lie vastly farther away. The familiar constellations that ancient humans named contain stars scattered across hundreds or thousands of light years of depth. Sirius, the brightest star in Earth's sky, blazes with a blue-white intensity that dominates winter evenings in the northern hemisphere. Ancient Egyptians based their calendar on its appearance, yet Sirius sits 8.6 light-years distant. The light you see from Sirius tonight departed that star in early 2017. When those photons began their journey, a different president occupied the White House, a different pope led the Catholic Church, and smartphones looked noticeably different. Sirius shows you conditions from nearly a decade ago. Vega, that brilliant blue-white star prominent in summer skies, lies 25 light-years away. The light arriving from Vega tonight began its journey around the turn of the millennium. Those photons departed when the September 11th attacks had not yet occurred, when the euro currency was newly introduced, when the human genome had just been sequenced. Vega shows you a star as it existed when the 21st century was barely beginning. Polaris, the North Star that has guided navigators for millennia, hangs roughly 430 light-years from Earth. Light travelling from Polaris toward you tonight began its journey when Shakespeare was writing his greatest plays. Those photons left their source when Queen Elizabeth I ruled England, when the Spanish Armada had recently been defeated, when European explorers were charting coastlines across the globe. Polaris shows you a star as it appeared during the late Renaissance. By the time light from Polaris reaches your eyes, over 4 centuries of human history have unfolded. Scientific revolutions have transformed human understanding. Technological civilizations have emerged from agricultural societies. The light you see represents a cosmic time capsule from an era when telescopes had not yet been invented. The stars you casually observe on any clear night represent time capsules spanning not just centuries but millennia. Betelgeuse, that red supergiant marking Orion's shoulder, lies approximately 700 light-years distant. The light you see from Betelgeuse departed shortly after Dante had completed the Divine Comedy. when the medieval world was reeling from the Great Famine, when the 100 Years' War between England and France was about to begin. If Betelgeuse exploded tonight in a supernova visible from Earth, humans would not witness that explosion for 700 years. The star could be gone already. We would have no way to know. Rigel, the blue supergiant at Orion's foot, sits roughly 860 light-years away. Its light departed during the height of medieval Europe, when the Crusades were reshaping the Mediterranean world, when the Song dynasty ruled China. Deneb, that brilliant star in the constellation Cygnus, lies approximately 2,600 light-years distant. Its light began travelling toward Earth when the ancient Greeks were colonizing the Mediterranean, when the Buddha was teaching in India, when the Persian Empire under Cyrus the Great was rising to dominate the ancient world. Extend your gaze to the limits of naked eye visibility, and the distances become even more extreme. Under dark skies, far from city lights, human eyes can detect the Andromeda galaxy as a faint smudge, barely visible without optical aid. Most people have never seen it. Most people do not realize they can see another galaxy with their naked eyes. Yet this ghostly glow represents light from over 1 trillion stars, located 2.5 million light-years from Earth. 2.5 million light-years. Light travelling at 186,000 miles per second for 2.5 million years. We see only where it was when our ancestors were still mastering stone tools, when Australopithecines roamed African plains barely distinguishable from other great apes. You cannot see Andromeda as it exists today. You see Andromeda as it existed 2.5 million years ago. The galaxy approaching our Milky Way right now might look completely different from the ancient image reaching your eyes. Stars have formed and died during that interval. Supernovae have exploded. Black holes have consumed matter. Civilizations might have risen and fallen. Entire stellar populations have evolved during the time those photons traveled toward Earth. This temporal displacement creates one of astronomy's most fundamental paradoxes. Every observation of distant space is simultaneously an observation of ancient time. The farther you look, the further back in history you see. This is not a limitation of instruments or technology. It is a consequence of the finite speed of light itself. Information cannot reach us faster than photons can travel. Powerful telescopes peer billions of light-years into space, revealing galaxies as they existed billions of years ago. The Hubble Space Telescope photographed galaxies whose light departed over 13 billion years ago. When the universe was less than 500 million years old, the James Webb Space Telescope has pushed even further, detecting light from the first galaxies to form after the Big Bang. These observations show cosmic infancy, conditions utterly unlike anything existing anywhere in the modern universe. The most distant objects ever observed show us conditions when the universe was less than 5% of its current age. We see a cosmos of chaos and formation, of infant galaxies colliding and merging, of stars forming at rates far exceeding modern cosmic activity. None of this exists anymore. The universe has evolved for 13 billion years since those conditions prevailed. The images we celebrate as cutting-edge discoveries show a cosmos that has been dead for longer than Earth has existed. But here lies the critical realization that should fundamentally shift your understanding of cosmic scale. Light, moving at the maximum speed physics allows, the fastest velocity anything can achieve in our universe, still requires billions of years to cross observable cosmic distances. The observable universe spans approximately 93 billion light-years in diameter. Even at 670 million miles per hour, light needs almost the entire age of the universe to traverse this cosmic expanse. The Milky Way galaxy alone stretches roughly 100,000 light-years from edge to edge. Our galaxy contains somewhere between 100 billion and 400 billion stars, each separated from neighbours by light-years of empty vacuum. If an alien civilization on the far side of our galaxy sent us a message tonight, using radio waves or lasers or any technology that transmits at light speed, our descendants would need to wait 100,000 years for it to arrive. 100,000 years. Modern humans emerged roughly 300,000 years ago. 100,000 years ago, our ancestors were developing early language, creating sophisticated stone tools, spreading across Africa into new territories. The entire span of human cultural evolution fits within the time a message would take to cross our single galaxy. If humanity replied immediately upon receiving such a message, another 100,000 years would pass before aliens received our response. A simple exchange of greetings would span 200,000 years of waiting. Recorded human history encompasses roughly 6,000 years. A single communication exchange across our galaxy would span 33 times longer than all of recorded history, 33 times longer than every pharaoh, every emperor, every written document, every civilization humanity has produced. This is why the speed of light is not fast. Measured against human experience, light seems impossibly swift. It illuminates rooms instantly. It enables telecommunications across continents. It carries your voice to satellites and back without perceptible delay. For every practical application humans have ever devised, light speed might as well be infinite. But measured against cosmic distances, light crawls. It trudges. It barely inches forward through the vast, empty spaces separating stars, galaxies, and cosmic structures. The distances that matter for any species hoping to engage with the cosmos require timescales that mock light speed's supposed swiftness. Every cosmic structure reveals the same fundamental truth. The distances between significant objects exceed what light can reasonably traverse. The solar system that seems so vast to human explorers spans roughly 12 billion miles from the Sun to the heliopause, where solar wind meets interstellar space. Light crosses this entire distance in about 18 hours, but our galaxy, containing 400 billion stars, would require 100,000 years for light to traverse. The local group of galaxies, our cosmic neighborhood containing the Milky Way, Andromeda, and several dozen smaller galaxies, spans roughly 10 million light-years. Light requires 10 million years to cross it. 10 million years ago, human ancestors had not yet diverged from the lineage leading to modern chimpanzees. 10 million years represents a span that exceeds the entire existence of anything recognizably human. The observable universe would require billions of years for light to traverse. Billions of years during which stars are born and die, during which galaxies collide and merge, during which civilizations could rise, flourish, and collapse into forgotten history. The fastest thing in existence still moves too slowly to cross the cosmos in any time frame meaningful to biological life. Scientists have searched exhaustively for particles traveling faster than light. Every experiment has confirmed that nothing exceeds this cosmic speed limit. Photons travel at exactly light speed. Gravitational waves propagate at exactly light speed. It is the maximum rate at which any causal influence can propagate through the universe. Matter, with mass faces even stricter constraints. It can approach, but never reach light speed. The closer anything gets to this barrier, the more energy required for additional acceleration. The relationship follows a curve that climbs toward infinity as velocity approaches light speed. Accelerating even a single kilogram to 99% of light speed would require energy exceeding the annual output of human civilization by enormous factors. Reaching 100% remains forever impossible regardless of energy expenditure. This speed limit is not arbitrary. It is not a technological barrier that sufficiently advanced civilizations might overcome. It emerges from the fundamental structure of space-time itself. Einstein's special relativity revealed that space and time are not separate entities but interconnected dimensions forming a unified fabric. The speed of light represents the maximum rate at which causality can propagate through this fabric. Exceeding light speed would mean arriving at a destination before you departed. It would mean receiving responses before sending questions. It would mean effects preceding causes. The logical structure of reality would unravel. Time itself would become incoherent. Physics does not merely suggest that nothing travels faster than light. Physics demands it. The mathematical framework describing our universe becomes inconsistent, contradictory, and meaningless if faster-than-light travel is permitted. The cosmic speed limit is woven into the fabric of existence itself. No civilization, however ancient or sophisticated, can break laws embedded in the geometry of space-time. The speed of light represents not what we have failed to exceed, but what cannot be exceeded by any process operating within our universe. This creates a universe where isolation is the default state. Every star exists in profound loneliness, separated from neighbors by gulfs that even light requires years to cross. Every galaxy floats through cosmic space, surrounded by voids that stretch millions of light years in every direction. Every cosmic structure inhabits a realm of emptiness, punctuated by occasional distant companions. The night sky creates an optical illusion suggesting cosmic crowding. Stars appear clustered together, separated by tiny angular distances from our perspective. The Pleiades cluster appears as a tight grouping of bright stars. The Milky Way appears as a dense band stretching across the sky. Everywhere you look, stars seem packed together in cosmic abundance. But this apparent proximity masks true physical separation. Those stars scattered across your field of view occupy three-dimensional space spanning thousands of light-years of depth. They appear close only because our eyes cannot perceive depth across interstellar distances. We see angular separation projected onto a two-dimensional sky, not actual spatial relationships in 3 dimensions. If you could shrink our solar system until the Sun became the size of a basketball, Earth would become a small bead orbiting roughly 26 yards away. Jupiter would be a marble at 130 yards. The entire solar system out to Neptune would fit within a large sports stadium. And the nearest star would be another basketball located approximately 4,000 miles away, roughly the distance from New York to Berlin. Everything between these basketballs, the overwhelming majority of interstellar space, contains essentially nothing but vacuum, radiation, and scattered atoms so sparse they make laboratory vacuums seem crowded by comparison. The best vacuums human technology can create still contain millions of atoms per cubic centimeter. Interstellar space contains perhaps 1 atom per cubic centimeter. The void between stars is emptier than any emptiness humans can manufacture. Light crosses these vacant spaces at its maximum cosmic velocity. Yet even moving at 670 million miles per hour, photons require years to bridge the gaps between neighboring stars. They require millennia to cross significant portions of our galaxy. They require millions of years to reach the nearest galaxies beyond our own. They require billions of years to traverse the observable universe. The speed of light defines the largest possible rate of cosmic communication. No message can travel faster. No signal can arrive sooner. No information can propagate more quickly through the vacuum of space. Yet this maximum rate renders meaningful communication nearly impossible across the distances that actually separate cosmic objects. The universe's speed limit is too slow for the universe's size. This paradox defines cosmic existence. The fastest motion possible still fails to bridge the gaps between significant structures in any reasonable time frame. The cosmos is too vast for its own physics. The distances between interesting destinations exceed what the maximum velocity can meaningfully traverse. Human intuition rebels against this conclusion. We see light illuminating rooms instantly. We experience telecommunications crossing continents in milliseconds. We watch laser beams appearing to leap instantaneously between points. Our lived experience suggests light moves infinitely fast compared to human needs. Our brains refuse to accept that this same seemingly instantaneous phenomenon represents an inadequate crawl at cosmic scales. But human needs operate at human scales. Cosmic reality operates at cosmic scales. And at cosmic scales, light speed represents a velocity so slow that the universe operates more like a vast collection of isolated islands than a connected cosmic community. Each star exists in solitary confinement. Each galaxy floats beyond meaningful contact with neighbors. Each civilization that might exist anywhere in the cosmos faces identical isolation regardless of technological achievement. This is the true nature of light speed. Not the impossibly fast phenomenon our intuition perceives, not the ultimate velocity that should connect everything instantly, but the tragically slow crawl that physics permits. The maximum that still falls catastrophically short of what cosmic connection would require. The speed limit that creates prisons rather than highways. The universe built itself on scales that mock its own speed limit. Every cosmic distance dwarfs what light can reasonably traverse. Every cosmic structure exists beyond meaningful contact with its neighbors. Every cosmic observation reveals ancient history rather than current reality. And every civilization that evolves sufficient intelligence to measure these distances eventually confronts the same devastating realization. The speed of light is ridiculously slow. The cosmic speed limit transforms the universe into a prison with cells measured in light years. Every star system exists in solitary confinement, separated from neighbors by walls that even light requires years to penetrate. Every galaxy inhabits its own isolated ward within a cosmic penitentiary spanning billions of light years. This is not metaphor. This is the mathematical reality of existence in a universe where the fastest possible motion still crawls across the distances that matter. Consider what interstellar travel would actually require. Science fiction depicts starships warping between solar systems in hours or days. Characters discuss visiting alien worlds as casually as humans discuss weekend trips. The Enterprise crosses the galaxy in television episodes lasting 42 minutes. These narratives have poisoned our intuition about cosmic distances and the brutal mathematics of crossing them. The nearest star system to our Sun is Alpha Centauri, a triple star system lying 4.37 light-years distant. That distance translates to roughly 25 trillion miles. If you started walking toward Alpha Centauri at a steady 3 miles per hour, never stopping to rest, eat, or sleep, you would arrive in approximately 950 billion years. The universe itself has only existed for 13.8 billion years. Walking to the nearest star would require roughly 70 times longer than cosmic history. Conventional rockets offer no salvation. The Saturn V rocket that carried astronauts to the Moon achieved speeds of roughly 25,000 miles per hour. At that velocity, reaching Alpha Centauri would require 115,000 years. The civilization that launched the mission would need to survive longer than modern humans have existed as a species, just to receive confirmation that the spacecraft arrived. Even our fastest spacecraft, the Parker Solar Probe, achieving 430,000 miles per hour during its closest solar approaches, would need roughly 6,700 years to reach Alpha Centauri. The Egyptian pyramids were built approximately 4,500 years ago. A spacecraft launched when the first pharaohs ruled would still have 2,000 years of travel remaining before reaching our closest stellar neighbor. Nuclear pulse propulsion, the most powerful theoretical rocket technology ever seriously studied, might achieve speeds of 3 to 5% of light speed. Project Orion in the 1950s and 60s proposed spacecraft propelled by nuclear bomb explosions, riding successive detonations to velocities far exceeding chemical rockets. At 5% of light speed, roughly 33 million miles per hour, the journey to Alpha Centauri would still require approximately 87 years. 87 years, a human lifetime. Anyone boarding such a vessel as an infant would arrive. As an elderly person, if they survived at all, the ship would need to function perfectly for nearly a century while traversing the radiation-filled void between stars. Any malfunction, any system failure, any medical emergency would unfold in absolute isolation, with Earth unable to provide assistance across the 4-year communication delay. But 87 years assumes technology humanity has never built and may never develop. The engineering challenges of nuclear pulse propulsion remain staggering. The political obstacles of launching thousands of nuclear weapons into space seem insurmountable. Even optimistic projections place such technology centuries in our future, if it ever becomes feasible at all. More speculative propulsion concepts offer marginally better numbers at the cost of even greater implausibility. Antimatter rockets could theoretically achieve higher fractions of light speed, but producing antimatter requires more energy than it releases, making such engines thermodynamically absurd for practical spacecraft. Fusion rockets might eventually propel ships to 10 or 15% of light speed. But sustained fusion remains beyond human engineering, despite decades of research. The breakthrough propulsion physics that science fiction casually invokes does not exist. Warp drives require exotic matter with negative mass, a substance that violates known physics and has never been observed. Wormholes require stabilization by materials that may be mathematically impossible. Hyperspace, subspace, and jump drives have no basis in any physical theory. They are narrative conveniences invented by storytellers, frustrated by the actual mathematics of interstellar travel. This leaves humanity, and presumably any other technological civilization, confined by the brutal arithmetic of relativistic travel. Even approaching significant fractions of light speed demands energy expenditures that strain credulity. Accelerating a modest spacecraft to 50% of light speed requires energy equivalent to the annual output of human civilization multiplied by thousands. The faster you want to go, the more energy you need, with requirements climbing toward infinity as you approach light speed itself. Einstein's special relativity explains why. As any object with mass accelerates toward light speed, its relativistic mass increases. This increased mass requires more force to accelerate further. The relationship follows a curve that rises toward infinity as velocity approaches the speed of light. No finite amount of energy can push any massive object to light speed. The barrier is not technological, it is mathematical. This creates a cosmic speed trap with no escape. The distances between stars require centuries or millennia to cross at achievable velocities. The energy requirements for higher speeds exceed practical limits by factors of millions. The theoretical maximum speed remains forever out of reach due to fundamental physics. Any civilization anywhere in the universe faces identical constraints. Whether they evolved 3 billion years before Earth formed, or will emerge 3 billion years after our sun dies, they confront the same relativistic mathematics. Advanced technology can approach the light speed barrier more closely, but no amount of scientific progress can break through it. The prison has no backdoor. The psychological reality of interstellar travel deserves contemplation beyond mere numbers. Imagine being born aboard a generation ship, a vessel launched centuries before your birth toward a star your great-great-grandparents selected from astronomical catalogues. You would live your entire life inside a metal cylinder hurtling through absolute darkness. You would never feel wind on your face except from artificial ventilation. You would never see a horizon except on screens displaying simulations. You would grow old and die knowing that your grandchildren's grandchildren might someday walk on solid ground beneath an alien sun. The people who arrive at distant stars would share almost nothing with those who departed. Centuries of isolated cultural evolution would transform language, values, social structures, and perhaps biology itself. The colonists who finally step onto alien soil would be descendants in only the most technical genetic sense. They would be aliens themselves, shaped by the strange environment of their traveling prison, adapted to conditions their ancestors never imagined. Generation ships would become worlds unto themselves, with their own histories, their own myths, their own sense of identity. The original mission might fade into legend, a founding story told to children who cannot truly comprehend that their ancestors once lived on a planet called Earth beneath a yellow star. The destination would become abstract, a promised land that older generations never expected to see personally. And throughout those centuries of travel, the void outside would offer nothing. No landmarks to mark progress, no scenery to observe. nothing but the faint light of distant stars that grow imperceptibly closer over human lifetimes. Travelers would measure their journey not in miles covered, but in generations elapsed, counting progress through births and deaths rather than distance traversed. The implications for interstellar colonization devastate common assumptions about galactic expansion. Science fiction depicts humanity spreading across the galaxy in waves of colonization, each settled world sending out new expeditions to nearby stars, the frontier advancing steadily outward until the entire Milky Way falls under human influence. The mathematics forbid this scenario. Consider a colony ship traveling at 10% of light speed. Itself, an extraordinary achievement, far beyond current capability. The journey to a star 40 light-years distant would require 400 years. Generations would live and die aboard the vessel. The colonists who arrived would be the great-great-great-great-great-great-great-grandchildren of those who departed. Cultural, linguistic, and even biological drift would accumulate across those generations. The people who landed would share little with the civilization that launched them. Once established, this distant colony could not maintain meaningful contact with Earth. Messages would require 40 years to travel between worlds. A question sent from Earth would receive a response 80 years later. No conversation is possible. No coordination is feasible. No political unity is sustainable. Earth and its colony would evolve independently, their cultures diverging faster than their messages could arrive. Now multiply this scenario across thousands of potential colony worlds. Each colony becomes effectively independent upon founding. Each develops its own culture, technology, and political system in isolation. Each colony that launches its own expeditions creates further fragmenting branches. Within a few millennia, any original connection dissolves into myth and legend. The galaxy cannot be unified under any single civilization. The communication delays exceed the timescales on which societies remain stable. The travel times exceed the timescales on which cultures maintain coherence. Any attempt to build a galactic empire would immediately fragment into countless isolated components, each evolving independently, each eventually forgetting their common origin. This fragmentation explains something profound about cosmic evolution. Even if technological civilizations are common, even if thousands of species achieved interstellar travel, they could not have built anything like unified galactic societies. The light speed barrier guarantees fragmentation. The prison guarantees isolation. No matter how advanced a civilization becomes, it cannot overcome the fundamental geometry of space-time. The galaxy could therefore contain thousands of intelligent civilizations, each searching the sky for companions, each broadcasting hopeful messages into the void, each waiting for responses that will never arrive in meaningful timeframes. The cosmic speed limit transforms a potentially crowded galaxy into a collection of isolated islands, each unaware of neighbors scattered across the galactic disk. This isolation offers a simple explanation for why we have detected no obvious signs of alien activity despite the galaxy's age and the abundance of stars. Consider an even more haunting possibility. What if we detected a signal tomorrow? What if our radio telescopes captured an unmistakably artificial transmission from a star system 5,000 light-years away? The discovery would transform human civilization, that we are not alone in the universe, but the beings who sent that signal transmitted it 5,000 years ago, when humans were just developing bronze tools and building the first cities. Any civilization we tried to respond to might have been extinct for millennia by the time we received their message. We would be reading letters from ghosts, studying the communications of beings who died before our species developed writing. Our response would race toward their world at light speed, arriving 10,000 years after we sent it, to find what? Ruins? Evolved descendants who no longer monitor those frequencies? A planet sterilized by cosmic catastrophe? The cosmos might be filled with such ghost signals, transmissions from civilizations that flourished and died while their messages traveled between stars. We might someday compile an archive of extinct cultures, a cosmic cemetery of beings we can never meet, whose thoughts we can only study as archaeological artifacts. The universe would become a museum of the dead, its exhibits preserved in electromagnetic radiation that continues propagating long after its creators have turned to dust. The isolation extends beyond communication to observation itself. You cannot see the universe as it currently exists. Every photon reaching your eyes carries information from the past. The depth of that past increases with distance. Look at the sun, and you see it as it was 8 minutes ago. Look at Alpha Centauri, and you see conditions from 4 years past. Look at the Andromeda Galaxy, and you observe it as it existed when our ancestors were still learning to walk upright. Even the Andromeda Galaxy, our nearest major galactic neighbour, lies so far away that the light reaching us tonight departed 2.5 million years ago. We cannot see Andromeda as it exists today. We see only where it was before modern humans had evolved, when our distant ancestors still roamed the African savanna. The actual current state of our closest galactic companion remains hidden behind an information barrier that light speed creates. This temporal displacement creates fundamental limits on cosmic knowledge. You can never know the current state of any distant object. You can never verify whether a star you observe tonight still exists. You can never confirm whether a distant galaxy has maintained its structure or been disrupted by cosmic events during the time its light traveled toward you. The James Webb Space Telescope peers billions of light years into space, revealing galaxies as they appeared when the universe was young. These observations show cosmic conditions from over 13 billion years ago. The galaxies we photograph have evolved for 13 billion years since emitting the light we capture. They may have merged with neighbours, been stripped of stars by gravitational interactions, or been consumed by larger structures. The images we celebrate as cosmic discoveries show ancient history, not current reality. Every astronomical observation is an act of archaeology rather than journalism. We study the past because the present remains hidden behind light travel delays. We excavate cosmic history from photons that departed their sources before Earth existed. We reconstruct ancient conditions from radiation that has traveled longer than life has existed on our planet. The cosmos reveals its history willingly, but guards its present state behind walls of distance that even light requires eons to penetrate. This limitation applies universally. Any technological civilization anywhere in the cosmos faces identical constraints. They can observe distant regions of their universe, but only as those regions existed in the past. Perfect knowledge of current cosmic conditions is impossible in principle. The speed of light guarantees that all observers exist in a state of perpetual ignorance about the present state of distant reality. The practical consequences cascade through every aspect of cosmic understanding. Astronomers studying stellar evolution must piece together stars at different life stages, spread across different distances, each observed at a different point in cosmic history. They cannot track a single star through its life cycle. Because that life cycle spans billions of years, they construct models by assembling snapshots from different objects at different distances, hoping the compilation accurately represents evolutionary sequences. Cosmologists studying the universe's large-scale structure face similar challenges. The cosmic web of galaxies, filaments, and voids they map represents not a single moment in time, but a composite spanning billions of years. Nearby regions show relatively recent conditions. Distant regions show ancient conditions. The maps blend different cosmic epochs into single images that never actually existed as unified states. This temporal smearing affects predictions about cosmic events. Astronomers know that Betelgeuse will eventually explode as a supernova. They can estimate that this explosion will occur within the next 100,000 years, but they cannot determine whether it has already happened. Light from Betelgeuse takes roughly 700 years to reach Earth. If the star exploded 600 years ago, we would have no way to know. The supernova's light would be racing toward us right now, carrying news of stellar death that we remain completely ignorant of. The same uncertainty applies to every potentially dangerous cosmic event. Gamma-ray bursts, magnetar flares, nearby supernovae. Any of these could threaten Earth if oriented toward us and close enough. But we cannot detect them until their effects arrive. No early warning is possible because the warning travels at the same speed as the danger. Light brings news of cosmic disasters at the same moment it brings the disasters themselves. This creates an unsettling vulnerability for any civilization anywhere in the cosmos. Extinction-level events could be racing toward inhabited worlds right now, their lethal radiation outpacing any possible warning. The universe offers no cosmic weather service, no advance notice of approaching storms. The prison does not merely isolate its inmates. It blinds them to approaching threats. The blindness extends to cosmic opportunities as well. If a habitable world exists around a nearby star, we cannot know its current conditions. We can observe that star and potentially detect planets in its habitable zone. We can analyze atmospheric spectra for signs of life. But all our observations show conditions from years or decades past. The world we study might have been sterilized by asteroid impact, consumed by stellar flare, or transformed by intelligent activity during the interval between observation and potential visit. Any interstellar colonization effort would navigate by outdated maps. Explorers would depart toward destinations known only through ancient light. They would spend decades or centuries traveling to worlds that might have changed dramatically since observations were made. The colony ship that departed toward a promising habitable world might arrive to find conditions completely different from those expected, with no possibility of redirecting to alternatives during the journey. The cosmic prison operates through information deprivation as much as physical confinement. Its inmates cannot gather intelligence about distant regions. They cannot verify conditions before committing to voyages. They cannot update their understanding of the cosmos in real time, because real time does not exist across interstellar distances. Every civilization operates with outdated information, making decisions based on observations of how things were rather than how things are. Human civilization has existed for perhaps 10,000 years, if you count the earliest agricultural settlements. Technological civilization, capable of detecting exoplanets, has existed for roughly 30 years. The oldest light we have detected, showing exoplanets, departed those worlds before modern humans developed agriculture. We are infants, in cosmic terms, examining the universe through observations of ancient events while remaining ignorant of current conditions. Any hope of cosmic engagement requires accepting these limitations. We cannot have real-time conversations with alien civilizations. We cannot know the current state of distant worlds. We cannot receive advance warning of cosmic threats. We cannot verify conditions before attempting interstellar voyages. The speed of light imprisons us in a bubble of local knowledge, surrounded by vast darkness, about which we can only receive delayed, outdated information. The prison metaphor actually understates the confinement. A prisoner can at least see the guards, communicate with other inmates, and observe the world beyond their cell through windows. Cosmic isolation offers no such amenities. The walls between stellar systems are not merely difficult to cross. They are thick with years or centuries of delay that prevent meaningful observation or communication. Two civilizations in the same galaxy might develop simultaneously, achieve technological sophistication within millennia of each other, and never have any way to know the other exists. Their signals would cross in the cosmic void, each arriving at the other's world long after the sending civilization had transformed beyond recognition. They would be neighbors in space, but separated by unbridgeable gulfs in time. This temporal separation creates a cosmos of ghosts. Every distant object we observe represents a message from the past, a time capsule sent by a universe that has since evolved. The stars we see tonight emitted their light when human history was unfolding differently, or before humans existed at all. We observe a gallery of ancient portraits while the subjects have long since aged, died, or transformed. Human religions often promise eternal consciousness, existence beyond the brief flicker of mortal life. Light that departed Alpha Centauri when you were born will not reach Earth until after you die. Photons that left distant galaxies when dinosaurs roamed will arrive when our species has been extinct for millions of years. We contribute to observations that we will never complete. Every civilization faces this asymmetry between observation and existence. They can begin studies that their species cannot finish. They can detect signals from civilizations that ceased to exist before the signals arrived. They can learn about cosmic events that occurred before their species evolved. The cosmos provides information without context, data without timeliness, knowledge without relevance to present conditions. This is the prison of distance, not merely the challenge of crossing vast empty spaces, though that challenge remains insurmountable. The deeper confinement involves the impossibility of knowing what lies beyond your local bubble of immediate observation. Every star system exists in an information desert, receiving only delayed news of a cosmos that has moved on without waiting for your understanding to catch up. The speed of light creates this prison by establishing the maximum rate at which information can propagate. No message can travel faster. No observation can be more current than the light travel time allows. No action can influence distant events until the delay has elapsed. The universe operates on cosmic timescales while its inhabitants are confined to local experience. Human ambition dreams of cosmic significance, of species that spread across galaxies, of civilizations that persist for billions of years, of intelligence that comes to understand and perhaps influence cosmic evolution. The light speed barrier mocks these ambitions. It confines every civilization to a tiny fraction of cosmic space, surrounded by vast territories they can observe but never reach, study but never visit, communicate with but never converse. And if you think this static picture of cosmic isolation seems bleak, wait until you understand how the expanding universe makes the prison contract around us over time. Space itself is stretching. Right now, as you read these words, the fabric of the universe is expanding in every direction. The room you occupy is expanding. The distance between atoms in your body is expanding. The space between Earth and the Moon is expanding. You do not notice because gravity and electromagnetic forces overpower expansion at local scales. But zoom out far enough, and expansion dominates everything. Galaxies drift apart like raisins in rising bread dough, carried by the growth of space itself rather than moving through it. This cosmic expansion does not merely add distance between objects over time. Expanding space makes the situation catastrophically worse. The universe is not just too large for its speed limit. It is growing larger while that speed limit remains fixed. Edwin Hubble confirmed cosmic expansion in 1929 through painstaking observations at the Mount Wilson Observatory in California. Using the largest telescope then available, Hubble measured the light from dozens of galaxies and discovered something remarkable. Distant galaxies appeared redder than nearby ones. Their light had been stretched toward longer wavelengths during its journey through space. This redshift indicated that space between us and distant objects was stretching, lengthening the wavelength of light, traveling through it. The effect resembled the Doppler shift that makes ambulance sirens sound lower pitched as they recede. But Hubble's redshift was different. Galaxies were not flying through space away from us like ambulances driving down roads. Space itself was growing, carrying galaxies along for the ride like dots painted on an inflating balloon. Hubble discovered that more distant galaxies showed greater redshifts. This relationship followed a precise mathematical pattern. Double the distance, and you double the recession velocity. Triple the distance, and you triple the velocity. This proportionality, now called Hubble's law, revealed that the entire universe was expanding uniformly in all directions. The expansion rate, measured by the Hubble constant, currently stretches space by approximately 70 kilometers per second for every megaparsec of distance. A megaparsec equals roughly 3.26 million light-years, a standard astronomical distance unit for intergalactic measurements. This means that galaxies 3.26 million light-years away recede at 70 kilometers per second due to expansion alone, independent of any motion through space. 70 kilometers per second might not sound impressive compared to light speed. It equals roughly 157,000 miles per hour, far slower than the 670 million miles per hour at which light travels. At first glance, expansion seems like a minor correction to cosmic distances, a small additional factor barely worth mentioning. But the Hubble relationship compounds with distance. Galaxies twice as far away recede at 140 kilometers per second. Galaxies 10 times farther recede at 700 kilometers per second. Galaxies 100 times farther recede at 7,000 kilometers per second. The recession velocity increases without limit as distance increases. This relationship continues linearly without any cosmic speed limit applying. At sufficient distance, the expansion of space carries objects away faster than light can travel toward us. Galaxies, billions of light-years distant, are receding at velocities exceeding light speed right now. The space between us and them stretches faster than any photon can cross it. This does not violate Einstein's prohibition on faster-than-light travel. Nothing is moving through space faster than light. The galaxies themselves drift through their local space at modest velocities, perhaps a few hundred kilometers per second at most. But space itself is stretching at rates that exceed light speed over large enough distances. The prohibition applies to motion through space, not to the expansion of space itself. Think of two ants crawling toward each other on a rubber sheet. If someone stretches the rubber faster than the ants can crawl, they will never meet despite both moving toward each other. Neither ant exceeds any speed limit. The rubber itself defeats their efforts. Cosmic expansion works identically. Light races toward us at maximum cosmic velocity, while space stretches beneath it faster than it can traverse. The critical threshold occurs at approximately 14 billion light-years from Earth, a distance called the Hubble radius or Hubble sphere. Beyond this distance, the cumulative expansion of all intervening space exceeds the speed of light relative to our position. Galaxies beyond the Hubble radius recede faster than light can approach us from their direction. This creates a cosmic horizon beyond which newly emitted light can never reach Earth. They will race toward us at light speed through their local space, while expansion carries them away faster than they can approach. The intervening distance stretches more rapidly than light can traverse it. Those photons are running on a treadmill that moves backward faster than they can run forward. Imagine standing on a conveyor belt moving away from a wall. If you walk toward the wall faster than the belt moves backward, you will eventually reach it. But if the belt accelerates, eventually it moves backward faster than you can walk. At that point, despite your continuous forward motion, you drift farther from the wall with every step. Light beyond the Hubble radius faces this exact situation. It travels toward us while falling behind, drifting into permanent exile despite racing at maximum cosmic velocity. The observable universe, therefore, has a finite boundary set by cosmic expansion rather than by the finite age of the universe alone. We often hear that we cannot see beyond a certain distance because light from farther regions has not had time to reach us since the Big Bang. Even given infinite time, light from beyond certain distances could never arrive because expansion defeats it. But the situation is actually much worse than this simple picture suggests. The expansion of space is not constant. It is accelerating. The universe is not merely growing, it is growing faster with each passing moment. The trap is tightening. In 1998, two independent research teams made the most surprising cosmological discovery in decades. Both teams were studying distant type Ia supernovae, stellar explosions that serve as cosmic distance markers because they all reach approximately the same peak brightness. By comparing how bright these supernovae appeared versus how bright they should have been at their measured redshifts, astronomers could determine whether cosmic expansion was slowing down as expected. Everyone anticipated finding deceleration. Gravity should pull matter together, gradually slowing expansion over cosmic time. The only question was whether enough matter existed to eventually halt and reverse expansion, causing a big crunch, or whether expansion would continue forever while gradually approaching zero velocity. Both teams found the opposite. Distant supernovae appeared dimmer than expected, meaning they were farther away than their redshifts indicated, meaning expansion had been slower in the past than it is today. Cosmic expansion was speeding up rather than slowing down. Something was pushing the universe apart against gravity's pull. Scientists named this mysterious force dark energy, a placeholder term acknowledging that nobody understood what it was. Subsequent observations confirmed dark energy's existence and measured its properties. It comprises roughly 68% of the universe's total energy content, dominating over both ordinary matter and dark matter combined. It behaves unlike any known substance, exerting negative pressure that drives accelerating expansion. The discovery earned the 2011 Nobel Prize in Physics for Saul Perlmutter, Brian Schmidt, and Adam Rees. But the prize recognized a finding, with deeply disturbing implications for cosmic futures. Accelerating expansion fundamentally changes the long-term fate of observation and exploration in the universe. With constant expansion, the cosmic horizon would remain at a fixed distance. Galaxies would cross beyond it as expansion carried them away, but new galaxies would continuously enter the observable universe from the opposite direction. The observable cosmic volume would remain stable even as individual objects drifted in and out. Accelerating expansion destroys this equilibrium. As expansion speeds up, the Hubble radius shrinks. The distance at which recession velocity equals light speed moves closer to us over time. Galaxies currently within observable range will eventually be carried beyond the horizon by accelerating expansion, lost to observation forever. No new galaxies will replace them, because the shrinking horizon means fewer objects remain within range. Consider what this means for any civilization observing the cosmos across vast timescales. The observable universe is not static. It represents a shrinking window of visibility that contracts as cosmic expansion accelerates. The night sky will progressively empty. The cosmic web we map will dissolve into darkness. The rate at which the cosmic horizon shrinks depends on dark energy's precise properties and expansion dynamics. The process seems slow by human standards, imperceptible across individual lifetimes, or even the entire span of human civilization. Over hundreds of billions of years, this gradual shrinking will dramatically reduce the observable universe. Over hundreds of billions of years, this shrinking horizon will dramatically reduce the observable universe. Calculations indicate that in approximately 100 billion years, the Virgo cluster, currently the nearest major galaxy cluster beyond our local group, will vanish beyond the cosmic horizon. Its thousands of galaxies will redshift into invisibility as expansion carries them beyond the reach of light. In approximately 2 trillion years, only galaxies within our local gravitational group will remain visible. The Milky Way, Andromeda, and the several dozen smaller galaxies gravitationally bound to them will constitute the entire observable universe. Everything beyond this small cluster will have crossed the cosmic horizon, carried away by expansion too rapid for light to overcome. The local group will have long since merged by that point. The Milky Way and Andromeda are currently approaching each other at approximately 70 miles per second, their mutual gravity overcoming cosmic expansion at our relatively small separation. In roughly 4.5 billion years, these two spiral galaxies will collide and merge into a single giant elliptical galaxy. Astronomers have nicknamed this future system Milkdromeda or Milkomeda. Future astronomers living in this isolated merged galaxy will observe an almost empty cosmos. Their most powerful telescopes will reveal only their own galactic system, plus whatever dwarf galaxies remain gravitationally bound. The billions of distant galaxies currently visible from Earth will have vanished entirely. Not hidden behind dust or dimmed by distance, but genuinely absent from the observable universe. These future observers will have no evidence that other galaxies ever existed. They might discover their own galaxy formed from a merger, finding dynamical evidence of two predecessor systems. But they would have no way to know that trillions of other galaxies once populated the visible sky. The cosmic web would be not merely invisible, but literally unimaginable. Even more disturbing, the cosmic microwave background radiation will have vanished by then. This faint afterglow of the Big Bang currently permeates all space, the oldest light in the universe, emitted when atoms first formed roughly 380,000 years after the Big Bang. We detect it today as microwave radiation with a temperature of roughly 2.7 Kelvin, just above absolute zero. Cosmic expansion continuously stretches this radiation toward longer wavelengths. The microwaves we detect today were originally visible light, then infrared, stretched across cosmic time into the microwave band. Accelerating expansion will continue stretching these wavelengths until they exceed any conceivable detection capability. The cosmic microwave background will shift into radio waves, then into wavelengths longer than planetary orbits, effectively vanishing from observability. Without the cosmic microwave background, future civilizations would lack the primary evidence for the Big Bang itself. They could not measure its properties to determine cosmic age, composition, or geometry. They would not see the primordial fluctuations that seeded galaxy formation. The baby picture of the universe would have been destroyed by the universe's own expansion. A civilization arising in this empty future cosmos would reach profoundly incorrect conclusions about reality. They would naturally assume they inhabited a small static universe containing only their local galactic system. They would observe no cosmic expansion because the only remaining objects would be gravitationally bound together, moving toward merger rather than apart. They would find no evidence for a Big Bang, no background radiation, no distant galaxies to suggest a larger cosmos. These future scientists might develop sophisticated physics, explaining their small eternal static universe. They would consider themselves successful at understanding cosmic reality. They would be completely wrong, deceived by the accident of when they evolved. The true cosmic history would be permanently hidden from them, erased by accelerating expansion. We currently live during a golden age of cosmic observation that will never return. The universe has existed long enough for light from distant regions to reach us, but expansion has not yet carried those regions beyond the cosmic horizon. We occupy a brief window in cosmic history when the evidence remains visible. We can see the cosmic microwave background and measure its properties precisely. We can observe galaxies at various evolutionary stages, from newly forming systems in the early universe to mature spirals and ellipticals nearby. We can measure expansion rates through multiple independent methods. We can piece together cosmic history from the Big Bang to the present day. All of this information will eventually become unavailable. This observational window will close. Accelerating expansion guarantees that future observers will have access to progressively less information about cosmic reality. The evidence we study today will gradually disappear. The cosmic microwave background will fade. Distant galaxies will redshift beyond detection. The expansion history that we measure will become unmeasurable. The universe is closing its blinds, gradually hiding its structure from any intelligence evolving after the current epoch. We happen to exist during the brief period when the blinds remain open. Future civilizations will inherit a cosmos that has concealed its own history. But accelerating expansion creates even more immediate problems than the eventual loss of cosmic evidence. Regions of space currently within our observable universe are already receding faster than light speed. We can see them only because their light departed when expansion was slower and they were closer. The most distant observable galaxies emitted their light over 13 billion years ago when the universe was less than 1 billion years old. Those galaxies were then only a few billion light-years away, close enough for their light to begin reaching us. But during the 13 billion years that light traveled, expansion carried those source galaxies vastly farther away. They now lie approximately 46 billion light-years distant. 46 billion light-years in a universe only 13.8 billion years old. This seems paradoxical until you remember that expansion accumulated throughout the light's journey. The universe was smaller when the light departed. It grew continuously as the light traveled. By the time photons completed their journey, their source had receded far beyond where it started. Those distant galaxies are currently receding at approximately 3 times the speed of light relative to Earth. Space between us and them stretches faster than any signal could cross. We will never receive any light they emit today. We see only their ancient past, captured in photons that escaped before expansion accelerated beyond light speed. This creates a profound asymmetry between what we can observe and what we can influence. We can see these distant galaxies. We can photograph them, measure their properties, study their ancient light, but we can never interact with them. Any signal we send in their direction will never arrive. Expansion will stretch the gap faster than our signal can traverse it. The light carrying information toward us crossed the cosmic horizon long ago, when expansion rates were lower and the journey remained possible. Our would-be response cannot duplicate that journey. Conditions have changed. The window has closed. Those galaxies transmitted their message successfully, but the return path no longer exists. The most distant objects in our sky are cosmic phantoms. We see images of galaxies that have since receded into eternal isolation, forever beyond any possibility of contact. The light reaching our telescopes represents a one-way transmission from a past that can never be revisited or contacted. We observe a universe that has already escaped beyond any possibility of interaction. Some cosmologists distinguish between the particle horizon and the event horizon to clarify this asymmetry. The particle horizon marks the boundary of what we can currently observe, set by how far light has traveled since the Big Bang. The event horizon marks the boundary of what we can ever influence, set by how far our signals can travel before expansion defeats them. These horizons do not coincide. The particle horizon lies much farther out than the event horizon. We can observe regions we can never reach. The visible universe vastly exceeds the reachable universe. Most of what we see has already escaped our cosmic grasp. Every galaxy in the visible cosmos falls into one of 2 categories. Those beyond our event horizon are already lost regardless of any action we take. Those within our event horizon are potentially reachable, but only through journeys spanning billions of years at significant fractions of light speed. Given the practical impossibility of such travel, even the reachable universe remains forever beyond human contact. The accelerating expansion that drives this isolation shows no sign of slowing. Observations of distant supernovae continue confirming acceleration. Measurements of the cosmic microwave background continue revealing dark energy's properties. Studies of baryon acoustic oscillations, sound wave patterns frozen into galaxy distributions, continue demonstrating that expansion speeds up over cosmic time. Dark energy appears constant, maintaining the same density as space expands. This constancy means its influence grows relative to matter, which dilutes as expansion spreads it thinner. Early in cosmic history, matter dominated, and gravity slowed expansion. Today, dark energy dominates, and acceleration prevails. The future belongs to ever faster expansion. Some theoretical models suggest even more extreme outcomes. If dark energy increases in density over time, rather than remaining constant, acceleration would eventually become so rapid that it overwhelms all other forces. This scenario, called the Big Rip, would see expansion overcome galaxy clusters, then individual galaxies, then solar systems, then planets, then atoms themselves. The universe would literally tear itself apart. Current observations slightly favor constant dark energy, making the Big Rip unlikely. But measurements contain uncertainties. Future observations might reveal that dark energy strengthens over time. If so, the cosmic trap would spring shut with violent finality rather than gradual suffocation. Even without the Big Rip, standard projections guarantee increasing isolation over cosmic time. The observable universe will shrink. Visible galaxies will vanish beyond the horizon. Evidence for cosmic history will disappear. Future civilizations will inhabit an increasingly empty cosmos with decreasing ability to understand it. This creates a cosmic countdown that any sufficiently advanced civilization must eventually confront. The universe provides a finite window for understanding its structure and history. Information available today will become unavailable over cosmic time. We possess knowledge that future civilizations cannot discover independently. We can measure the Hubble constant because distant galaxies remain visible. We can determine cosmic age because the cosmic microwave background remains detectable. We can map the large-scale structure of the universe because expansion has not yet erased it. Future civilizations arising after the evidence disappears would need to receive this knowledge from predecessors. But the same expansion that hides cosmic evidence would isolate civilizations from each other. Knowledge accumulated during the golden age of observation would be lost unless somehow preserved and transmitted across the vast gulfs opening between cosmic regions. This raises haunting questions about cosmic information preservation. Should civilizations attempt to transmit cosmic knowledge to isolated future observers? Could any message survive the billions of years separating our epoch from theirs? Would recipients even recognize or believe information about a cosmos that contradicts their direct observations? We are cosmic archaeologists studying a site that will be buried forever by the sands of expanding space. The artifacts we excavate today will be permanently destroyed. The evidence we document will be erased. Future archaeologists will have nothing to study because expansion will have removed all traces of what once existed. The speed of light was already too slow for the static distances between cosmic objects. Even without expansion, light required billions of years to cross the observable universe. Communication across cosmic distances remained impossible within the lifespan of any civilization. Expanding space makes the problem worse. The distances light must cross grow continuously larger. Destinations recede while travelers approach. Finish lines move away faster than runners advance. Accelerating expansion makes the problem catastrophic. The growth rate increases over time. Distances expand faster with each passing year. The cosmic trap does not merely confine, it contracts, squeezing the observable universe into an ever smaller cell, while simultaneously stretching the unobservable universe into ever larger exile. Every civilization anywhere in the cosmos faces this same trap. Physics enforces the speed limit everywhere. Cosmic expansion stretches all distances, regardless of location. Acceleration ensures the trap tightens for everyone. A civilization on the far side of the observable universe, 46 billion light-years distant, faces identical constraints. They cannot travel faster than light. They cannot escape their shrinking observable universe. They cannot preserve information about cosmic history any more than we can. Advanced technology offers no escape. Better telescopes can observe more distant objects, but expansion will still carry those objects beyond detection. Faster spacecraft can approach light speed more closely, but expansion will still outpace them at sufficient distances. More powerful transmitters can send clearer signals, but expansion will still prevent those signals from reaching destinations beyond the event horizon. The cosmic trap is not technological, it is geometric. It emerges from the fundamental structure of space-time itself. No amount of scientific progress can overcome mathematical impossibility. The universe is not merely large, it is expanding. It is accelerating. and it is systematically erasing itself from observation. The cosmos provides a brief window during which intelligent observers can glimpse its true scale and history. Then that window closes permanently. We exist within that window. We can see the evidence, we can measure the expansion, we can understand what we are losing. Future observers will inherit a universe that has hidden its own nature, a cosmos that destroyed the evidence of its own existence. The speed of light created a prison of distance. Cosmic expansion created a prison that shrinks. Accelerating expansion created a prison that crushes its inhabitants toward ever smaller observable volumes, while stretching the unobservable majority into ever greater isolation. This is the expanding trap. Not content to imprison cosmic civilizations, the universe ensures that prisons grow smaller over time. The walls close in, the horizons shrink, the evidence disappears, and there is nothing any civilization, anywhere, can do about it. The inadequacy of light speed shapes the fundamental character of existence throughout the cosmos. This is not merely a human problem or an earthly limitation. Every intelligent civilization that has ever evolved or ever will evolve anywhere in the universe confronts identical constraints imposed by physics itself. The implications extend far beyond inconvenient travel times or delayed communications. They define what types of cosmic societies can exist, what forms of knowledge are achievable, and what ultimate significance any civilization can possess. The Fermi paradox has haunted scientists since physicist Enrico Fermi posed his famous question over lunch in 1950. Given the enormous number of stars in our galaxy, given the billions of years available for evolution, given the apparent inevitability of technological development once intelligence emerges, where is everybody? The galaxy should be teeming with evidence of alien civilizations. Radio signals should fill the electromagnetic spectrum. Megastructures should be visible around distant stars. Probes should have reached our solar system long ago. Various proposed solutions attempt to explain the apparent cosmic silence. The rare Earth hypothesis suggests that conditions permitting complex life are extraordinarily uncommon, making Earth a statistical anomaly. The Great Filter hypothesis proposes that some obstacle prevents civilizations from becoming detectable, either behind us in evolutionary history or ahead of us as an existential threat. Self-destruction theories argue that technological civilizations inevitably annihilate themselves through nuclear war, environmental collapse, or artificial intelligence gone wrong. Zoo hypotheses suggest that advanced aliens deliberately conceal themselves from primitive species like humanity, but the speed of light itself provides a simpler explanation that requires no special assumptions about alien psychology, evolutionary barriers, or cosmic conspiracies. The galaxy could be filled with intelligent civilizations that cannot detect each other because light speed prevents meaningful contact across the distances that separate them. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy by multiplying factors representing star formation rates, planetary frequency, habitability, life emergence, intelligence evolution, technology development, and civilization longevity. But light speed affects nearly every term in this calculation in ways often overlooked. Consider civilization longevity. How long does a technological civilization typically survive? This question usually focuses on self-destruction risks, but light speed imposes its own constraints on civilization duration. A civilization must persist long enough to send messages across interstellar distances and receive responses. If the average technological civilization survives only 10,000 years, it cannot participate in exchanges spanning 50,000 light-years. The communication window closes before the conversation completes. Light speed also affects the detectability term. A civilization might broadcast signals for millennia, but those signals require additional millennia to reach potential listeners. If civilizations typically broadcast for only brief periods before falling silent, The signals might arrive long after the senders have ceased transmission. We could be surrounded by ancient signals from extinct civilizations, radio echoes of vanished beings who stopped listening before our responses could arrive. Imagine a civilization that arose 1 billion years ago, on the opposite side of our galaxy, roughly 100,000 light-years distant. This civilization had a billion-year head start on humanity. They developed technology when multicellular life on Earth consisted of simple worms and jellyfish. They built spacecraft when our ancestors were single-celled organisms. They contemplated the cosmos when nothing on our planet had yet evolved eyes to see it. Even with this enormous head start, even if they achieved technology capable of traveling at 99% of light speed, their expansion through the galaxy would require hundreds of thousands of years. Colonization ships departing their homeworld would need over 100,000 years to reach the far side of the galaxy where Earth resides. Generations beyond counting would live and die aboard those vessels. Entire civilizations would rise and fall during the journey. Signals they broadcast from their homeworld would fare no better. Radio waves or laser pulses transmitted toward our region of the galaxy would require 100,000 years to arrive. By the time any evidence of their existence reached our solar system, the civilization that sent it might have collapsed into barbarism, evolved into something unrecognizable, uploaded into computer substrates, or simply stopped transmitting. When those signals finally arrived, would humanity even exist to receive them? 100,000 years ago, modern humans were just beginning to spread beyond Africa. 100,000 years from now, will Homo sapiens still exist in any recognizable form? The communication timescales imposed by light speed exceed the duration of species, cultures, and possibly even planetary habitability. The galaxy could therefore contain thousands of intelligent civilizations, each searching the sky for companions, each broadcasting hopeful messages into the void, each waiting for responses that will never arrive in meaningful timeframes. The cosmic speed limit transforms a potentially crowded galaxy into a collection of isolated islands, each unaware of neighbors scattered across the galactic disk. Beyond mere isolation lies a more profound loss. Somewhere in the cosmos, if our assumptions about life's prevalence hold any validity, civilizations have developed knowledge we will never access. They have discovered scientific principles that would revolutionize our understanding. They have developed philosophies that would reshape our conception of meaning and existence. This cosmic library exists beyond our reach. The accumulated wisdom of potentially billions of intelligent species throughout cosmic history remains permanently inaccessible. We cannot browse its shelves. We cannot request interlibrary loans across the light years. Each civilization compiles its own knowledge in isolation, unable to benefit from the insights others have achieved. Consider what humanity might learn from a civilization 1 million years more advanced than us. They might have solved problems we have not yet formulated. They might understand physics at levels that would seem like magic to our scientists. They might have developed technologies that transcend our imagination. They might have answers to questions about consciousness, meaning, and existence that have plagued human philosophy for millennia. All of this potential knowledge exists somewhere in the cosmos if intelligent life is common. We are students in a universe filled with teachers we can never meet, libraries we can never visit, wisdom we can never absorb. Every civilization must begin from scratch, rediscovering principles that others have already mastered, reinventing solutions that others have already implemented. This isolation would persist regardless of technological advancement. Science fiction imagines that sufficiently advanced civilizations would develop faster than light, travel, subspace communication, or Ansible networks, enabling instant contact across any distance. These technologies make compelling stories but violate fundamental physics. A civilization 1 million years more advanced than humanity would still face identical light speed constraints. They might approach light speed more closely than we can currently imagine. They might develop more sensitive receivers and more powerful transmitters. They might build telescopes, capable of imaging exoplanet surfaces across thousands of light years. But they could not build faster than light communication systems because physics prohibits them. They could not establish instant contact with distant regions because space-time structure forbids it. They could not create unified galactic civilizations because communication delays would exceed the timescales on which any society remains stable. Consider what political unity requires. Governments must receive information about conditions in their territory. They must deliberate and reach decisions. They must transmit those decisions to affected regions. They must receive feedback about implementation. They must adjust policies based on outcomes. This cycle of communication, decision, implementation, and feedback defines governance at every scale, from village councils to planetary administrations. The maximum size of any coherent civilization is therefore limited by light speed and the timescales on which societies can tolerate decision delays. If a civilization requires decisions to be made and implemented across its territory within 100 years, then its maximum territorial extent cannot exceed roughly 50 light-years in radius. Beyond this distance, the round-trip communication time exceeds the decision cycle duration. 50 light-years encompasses approximately 1,400 stars in our galactic neighborhood. This represents a substantial interstellar civilization by any human measure, but it covers less than 1/1,000,000th of the galaxy's total volume. A civilization spanning 50 light-years would know nothing about conditions across 99.9999% of the Milky Way. Human history demonstrates how communication delays fragment political structures. Colonial empires, operating across oceans, faced communication delays of months that severely hindered centralized governance. When Spain ruled territories in the Americas, messages between Madrid and Mexico City required months of ocean travel in each direction. By the time colonial administrators received instructions from the Crown, local conditions had often changed dramatically. The American Revolution illustrated these dynamics starkly. News of the Boston Tea Party took weeks to reach London. Parliamentary deliberations required additional weeks. Instructions to colonial governors took more weeks to return across the Atlantic. By the time British authorities responded to colonial grievances, new grievances had accumulated, and colonial patience had expired. Communication lags, measured in months, contributed to the fragmentation of a global empire. Interstellar civilizations would face communication delays not of months but of decades, centuries, or millennia. No governmental structure humans have ever conceived could function coherently across such delays. A council deciding policy for a civilization spanning 1,000 light-years would issue instructions about conditions that existed during medieval times. They would receive feedback about the effects around the time the sun exhausts its hydrogen fuel. Different regions would inevitably develop distinct cultures, technologies, languages, and political systems. They would share common origins but diverge along independent evolutionary paths. After sufficient time, they would become alien to each other, despite their common ancestry. The concept of unified interstellar governance represents a fantasy incompatible with physics. This means that cosmic civilizations, if they exist, must take forms radically different from anything science fiction has imagined. They cannot be empires ruling multiple star systems through centralized authority. No emperor can govern subjects whose messages require centuries to arrive. They cannot be federations maintaining political unity across galactic distances. No federation can hold votes when delegates need millennia to receive ballots and return them. Interstellar civilizations can only exist as collections of isolated outposts, each evolving independently, connected by message exchanges spanning generations. These messages would resemble time capsules more than communications. They would carry news of events long concluded, questions about situations long resolved, answers to queries whose askers died centuries before responses arrived. Any advanced civilization contemplating these realities must eventually accept that cosmic unity is impossible. They cannot maintain interstellar relationships in any sense that biological beings would recognize as relationships. They cannot participate in cosmic communities because no such communities can exist. The speed of light condemns every intelligence to cosmic loneliness, regardless of technological achievement. This conclusion does not depend on assumptions about alien biology, psychology, or sociology. It follows directly from physics. The laws governing our universe prohibit the kinds of cosmic connection that intelligent beings naturally desire. This conclusion applies universally throughout the cosmos. Every galaxy and every supercluster throughout the observable universe contains civilizations, if any exist, facing identical constraints. The laws of physics do not vary between cosmic regions. Experiments conducted in distant galaxies would yield identical results to experiments conducted on Earth. Light speed remains constant everywhere. Cosmic isolation affects all intelligence equally. An alien civilization in the Andromeda Galaxy, 2.5 million light-years distant, confronts the same prison walls that confine humanity. They cannot communicate with us in any meaningful way. A message they sent today would arrive in 2.5 million years. Our response would require another 2.5 million years to reach them. 5 million years between question and answer. By any reasonable definition, that is not communication. But they also cannot communicate meaningfully with civilizations within their own galaxy. Andromeda spans roughly 220,000 light-years. Communication across their galaxy would require timescales exceeding the duration of most civilizations' existence. They are as isolated from their galactic neighbors as we are from ours. The implications extend to the nature of knowledge itself. Any civilization can only know about cosmic regions from which light has had time to arrive. Their knowledge is always incomplete, always outdated, always limited by the finite speed at which information propagates. Perfect cosmic knowledge is impossible in principle, not merely difficult in practice. A sufficiently advanced civilization could map their observable universe with extraordinary precision. They could catalogue billions of galaxies. They could measure cosmic expansion rates to many decimal places. They could understand the physics of stellar evolution, galactic dynamics, and cosmic structure formation. They could piece together the history of the universe from the Big Bang to their present epoch, but they could never verify that their observations represent current reality. They could never be certain that cosmic structure has not changed dramatically since the light they study began its journey billions of years ago. This epistemic limitation affects every form of scientific inquiry. Theories can only be tested using information that has arrived from studied regions. The assumption that physical laws operate uniformly throughout the universe cannot be directly verified for regions beyond the cosmic horizon. We assume that gravity works the same way in distant galaxies as it does locally. We assume that atoms behave identically everywhere. These assumptions seem reasonable and have never been contradicted by observations, but they remain assumptions extrapolated from local measurements, not confirmed through direct testing of distant regions. Some philosophers take these limitations further, arguing that regions beyond the cosmic horizon effectively do not exist from the perspective of any particular observer. If no information from a region can ever reach you, and you can never influence that region through any possible action, does its existence have operational meaning? This question touches on deep issues in philosophy of science. Existence claims that cannot be verified, even in principle, occupy an uncertain epistemological status. We believe the universe continues beyond our cosmic horizon because models that include continuous space match observations better than models with arbitrary boundaries. But we cannot point to evidence from beyond the horizon to support this belief. The speed of light, therefore, creates boundaries not merely on what can be known, but potentially on what exists in any operationally meaningful sense. The horizon defines a kind of existence boundary as surely as it defines an observation boundary. Reality beyond that boundary remains forever inaccessible, forever uncertain, forever beyond verification. The cosmic speed limit also shapes the ultimate fate of any civilization that survives long enough to contemplate cosmic timescales. As explored earlier, accelerating expansion shrinks the observable universe over time. Any civilization surviving into the far cosmic future will inhabit a cosmos that appears almost empty, containing only their local gravitational group. The evidence for cosmic expansion and distant galaxies will have been erased, leaving future intelligences unable to discover truths that we currently take for granted. We therefore inhabit a privileged epoch in cosmic history, though privilege might not be the right word. Current conditions allow us to observe the cosmic microwave background and measure its properties. We can see galaxies at various distances, representing various evolutionary stages. We can measure cosmic expansion through multiple independent methods. We can piece together cosmic history from observational evidence rather than pure speculation. This information will become permanently unavailable over cosmic time. The evidence we currently study will be systematically erased by accelerating expansion. Future civilizations will inherit a cosmos that has hidden its own history. They will be unable to discover what we already know because the evidence will have ceased to exist. This temporal situation carries no particular cosmic significance beyond the accident of when our civilization arose. We did nothing to deserve this observational window. We simply happened to evolve during the brief cosmic period when evidence remains visible. Had humanity emerged 50 billion years in the future, we would never have discovered cosmic expansion or the existence of other galaxies. Our scientific accomplishments partially reflect fortunate timing rather than unique capability. The speed of light defines the fundamental character of cosmic existence in ways that most people never contemplate. It creates isolation that no technology can overcome because the limitation is mathematical rather than engineering. It imposes ignorance that no scientific advancement can dispel because information simply cannot arrive faster than light permits. It guarantees loneliness that no civilization can escape because physics applies universally. Every star visible in the night sky represents a potential home for intelligence that will never meaningfully contact us, even if they exist. Every galaxy and telescope images might harbor billions of civilizations, forever unaware of our existence despite sharing the same universe. The cosmos potentially teems with neighbors separated by walls of light years that no signal can penetrate in any meaningful time frame. Human dreams of cosmic community rest on foundations that physics does not support. Contact with alien intelligences remains effectively impossible across interstellar distances, regardless of how powerful our transmitters become or how sensitive our receivers grow. Participation in galactic civilizations remains forbidden by the communication delays that would fragment any such civilization into isolated components. The maximum speed of information transfer is simply too slow for the minimum distances between cosmic objects. The universe was built on scales that mock its own speed limit. This architectural mismatch between cosmic distances and cosmic velocities defines what is possible for intelligence anywhere in existence. How should intelligent beings respond to this cosmic condition? Different civilizations might develop radically different philosophical frameworks for coping with cosmic isolation. Some might embrace what we could call cosmic stoicism, accepting the limitations of existence without despair and finding meaning within the boundaries physics permits. These civilizations would focus on perfecting their local domains, developing rich cultures, and deep understanding within the light years they can actually influence. Others might develop cosmic religion, interpreting light speed constraints as evidence of deliberate cosmic design. They might believe that isolation serves some purpose beyond mortal comprehension. They might find comfort in faith that connections impossible in physical reality continue in spiritual dimensions unbounded by light speed. Still others might turn toward cosmic despair, concluding that existence in an isolating universe lacks ultimate meaning. These civilizations might focus on immediate pleasures, abandon long-term projects, or even choose collective extinction rather than persist in meaningless isolation. The cosmic condition would defeat their will to continue. Some civilizations might find meaning in observation itself, even when participation remains impossible. They might dedicate themselves to understanding the cosmos they cannot join, finding purpose in knowledge even without application. These cosmic scholars would study distant galaxies they can never visit, catalogue alien biospheres they can never contact, and document cosmic history they can never influence. Humanity has not yet collectively confronted these questions. Most people remain unaware of how thoroughly physics constrains cosmic possibility. Popular culture continues depicting interstellar empires and galactic federations as though physics were merely a suggestion. The psychological reckoning with cosmic isolation remains in our future. Some people find the conclusion profoundly depressing. The cosmos seems almost maliciously designed to prevent exactly the cosmic connection that intelligent beings naturally desire. We evolve curiosity about what lies beyond our planet. We develop technology capable of detecting signals across interstellar distances. We dream of contact with kindred intelligences who might share knowledge, culture, and companionship across the cosmic void. And then we discover that physics forbids everything we hoped for. The universe offers us glimpses of cosmic grandeur while denying participation in it. We can see, but not touch. We can observe, but not interact. We can know that other worlds exist while being permanently unable to visit them. This cosmic tease strikes many people as cruel, a joke played on consciousness by an indifferent universe. Others find liberation in cosmic isolation. If we can never join cosmic communities, we need not worry about cosmic comparisons. Human achievements need not be measured against alien accomplishments we can never verify exist. Our significance derives from our own values and judgments rather than our standing in cosmic hierarchies we can never access. This perspective reframes isolation as freedom. No galactic empire will ever judge humanity primitive or advanced. No alien civilization will ever evaluate our art, our science, or our morality. We are cosmically alone, which means we are cosmically free to determine our own significance without external reference. The speed of light imposes humility on cosmic ambition, regardless of which perspective individuals find more comforting. Humanity will never rule interstellar empires because such empires cannot exist. We will never participate in galactic governments because light speed delays would make them incoherent. We will never know whether cosmic neighbors consider us worthy of attention because communication across those distances remains impossible. But this same constraint applies equally to every other civilization in the cosmos. They too face light speed limitations. They too cannot build galactic empires. They too experience cosmic isolation regardless of technological sophistication or evolutionary advancement. Humans are not uniquely confined. All intelligence everywhere shares identical constraints. The speed of light creates a universe of enforced equals. No civilization can achieve cosmic dominance because physics prevents the expansion of influence across interstellar distances. No intelligence can access greater cosmic truth because all observation remains limited by light travel time. No species can escape cosmic isolation because space-time geometry forbids faster than light anything. In this sense, the inadequacy of light speed represents a kind of cosmic democracy. Every intelligence faces identical constraints regardless of when or where they evolve. Every civilization inhabits the same type of cosmic prison with the same inescapable walls. Every species that achieves sufficient understanding eventually reaches the same devastating conclusions about cosmic existence. The universe does not play favorites, it confines all intelligence equally. The most ancient and advanced civilization imaginable remains as isolated as humanity. They have had more time to contemplate their prison, but they cannot escape it any more than we can. This equality offers strange comfort. We are not cosmically disadvantaged relative to any other intelligence. Our isolation reflects universal law rather than particular misfortune. Whatever other civilizations might exist, they share our condition. We are alone together, separated by distances we cannot cross but united by constraints we all share. The universe is not merely stranger than we imagine, it is stranger than we can imagine. And the strangeness begins with the simple fact that the fastest thing in existence moves too slowly to matter at cosmic scales. Light speed seemed like nature's gift when humans first measured it with rotating mirrors and careful timing. 670 million miles per hour. Nothing in human experience approaches such velocity. Nothing in nature moves faster. The cosmic speed limit represents the ultimate velocity anything can achieve within the laws of physics. But cosmic distances exceed what this ultimate velocity can meaningfully traverse. Stars are separated by years of light travel at minimum. Galaxies are separated by millions of years. The observable universe spans billions of light years in every direction, requiring billions of years for light to cross. The cosmic speed limit is too slow for the cosmos it governs. This single architectural fact shapes everything about what kind of universe we inhabit, what possibilities exist for cosmic life, and what ultimate fate awaits any intelligence anywhere. We exist as brief patterns of organized matter in one small corner of an enormous cosmos. We can observe distant regions through light that has traveled for billions of years. We can understand physical laws that govern cosmic evolution. We can contemplate scales that dwarf human experience by factors beyond comprehension. But we can never reach the cosmos we observe. We can never influence regions beyond our cosmic horizon. We can never participate in cosmic communities or join galactic civilizations. The speed of light permits observation while preventing participation. It enables knowledge while enforcing isolation. It allows us to see the universe while forbidding us from joining it. This is why the speed of light is ridiculously slow. Not because 670 million miles per hour fails to impress human intuition. At human scales, that velocity appears godlike. But cosmic scales are not human scales. Cosmic distances require velocities that physics categorically forbids. The universe built itself on scales that mock its own speed limit. Stars needed to be separated by light years rather than light seconds. Galaxies needed to span hundreds of thousands of light years rather than light hours. The observable cosmos needed to stretch billions of light years rather than millions. With smaller separations, light speed would have been adequate. Civilizations could have communicated across stellar distances in reasonable timeframes. Galactic communities could have formed. Cosmic connection could have been possible. But the universe did not build itself at convenient scales. It built itself at scales where its own speed limit becomes inadequate, where the fastest possible motion still crawls, where the ultimate velocity still fails. Every intelligence that ever arises anywhere in the cosmos eventually discovers this same devastating truth. They measure light speed and marvel at its swiftness. They measure cosmic distances and realize that swiftness is not nearly enough. They contemplate the mathematics and understand that no technology can overcome what physics forbids. Then they must decide how to live with that knowledge. How to find meaning in a cosmos that permits observation but forbids participation. How to build civilizations knowing that interstellar expansion remains effectively impossible. How to search for cosmic companions knowing that meaningful contact cannot occur. Humanity now faces these same questions. We have measured light speed. We have measured cosmic distances. We understand the mathematics well enough to know that faster than light travel violates fundamental physics. Some will continue dreaming of cosmic connection despite its impossibility. Hope dies hard, and human imagination resists physical constraints. They will imagine wormholes, warp drives, and dimension-hopping technologies that physics does not permit but stories require. Others will turn inward, focusing on human concerns across human scales. If the cosmos remains forever beyond reach, then human significance must be found within human contexts. Earth becomes not a launching pad for cosmic expansion but humanity's permanent home, worthy of care and cultivation across generations. Still others will find meaning in the observation that physics permits, even while forbidding participation. We can study the cosmos, even if we cannot join it. We can understand cosmic evolution, even if we cannot influence it. We can appreciate cosmic grandeur, even if we cannot touch it. Knowledge itself becomes the consolation prize for intelligence evolved in a universe too large for its speed limit. The night sky will continue inspiring wonder regardless of what we know about light speed limitations. Stars will still shine with ancient light that traveled years or millennia to reach our eyes. Galaxies will still glow with the combined luminance of billions of suns. The cosmic web will still stretch across observable space in patterns that reveal the universe's deepest structure, but that wonder will now carry melancholy undertones. Every beautiful object in the night sky exists beyond meaningful reach. Every star represents isolation we cannot overcome. Every galaxy contains potential neighbors we can never meet. The speed of light is ridiculously slow. Too slow for the cosmos it supposedly connects. Too slow for the civilizations that might want to communicate across it. Too slow for the dreams of cosmic community that intelligent beings naturally develop. 670 million miles per hour, the fastest velocity in existence, and nowhere near fast enough.